Welcome to the presentation. We are going to talk a little bit today about accelerating the EV adoption with the smart charging tools. First, let us introduce ourselves. My name is Pedro. I'm an associate professor at TU Delft, working on the intersection of AI with many of the current problems of the electricity infrastructure. And together here with Stavros.
Yeah, I'm a PhD student working with Pedro. My focus is on how we can use AI to solve large-scale optimization problems. In our case, we have the problem of charging a lot of electric vehicles, and we're going to show some things about that today.
Yes. Thank you, Stavros. So we will start a little bit with the problem, right? The large expected numbers of electric vehicles that are being deployed due to the transition of the mobility sector, right? We saw in the previous presentation the interface and the standards for the CPOs to communicate directly with these electric vehicles. We also saw in the previous presentation what happens with the electricity network, right? When we have these large numbers of electric vehicles demanding to be charged at the same time, which is a particular problem for the Netherlands, right? Huge demands of charging electric vehicles, which are causing this congestion, which is resulting in, for example, delays in requesting new connections due to the limited capacity of this infrastructure. So what we are going to present today relates to, let's say, our way of approaching the problem. We're going to introduce to you two tools that are in development in the European project DRIVE2X that we are working on. The first one is an environment called EV2Gym, which is a simulation tool to test large dispatch of a large number of electric vehicles. And the second one is a platform that is called EPIOT, which is focused on EV flexibility assessment. Yes, so before jumping into the first simulator, I wanted to express why do we need this smart charging simulator. I think that this is yours.
Yeah, I can take over. Thank you, Pedro. All right, so a few years ago, we started approaching this problem. We said, okay, we have all this nice, we have this nice problem. We have a lot of electric vehicles. How can we solve this problem from the perspective of research? We searched online, and we didn't find many simulators that were modular and that could be customizable as much as we wanted. So, as everyone is doing, we developed our own simulator. However, our vision is that we can have, let's say, a common testbed that many other people from research, maybe from industry, can go and compare their own implementations. This is the vision, at least. So we came up with EV2Gym. We released it maybe 1 year ago, 1.5. It's an open source tool. We focus on V2G-enabled simulation, so we also we allow the user to select almost everything. We support the Gym API, which allows to develop AI algorithms like reinforcement learning. Hence the name EV2Gym. And the idea is that we can develop any type of algorithm we want, for example, heuristics, optimization, and AI. But let's see what is it about. How does it look like? The idea is that we have a discrete time simulation. For example, we can simulate the whole day, divided in some discrete intervals, like 5, 10 minutes. It's up to us to decide. We have the configuration phase where we are going to put how the problem looks like. For example, how many electric vehicles we have, or how many chargers, actually. What are the specifications? Then we can also decide what is the charging topology, and actually also how the distribution network can look behind that, if we want to simulate the network as well. And very important, the EV behavior. In practice, we have some open source data from a lab. For example, we know what is the usual behavior for public chargers, or for workplace chargers, or for residential ones. But we could also have, let's say, some private data from a company. So this is why we'll allow the user to use any data they want. They can use the ones that are publicly available, or they can put their own. We also can allow the user to select charging prices, flat rates, or dynamic prices, whatever they want. So as the configuration is finished, now we go to the environment. As you can see, we have a lot of different assets. We have the chargers that are waiting there, they're instantiated, and then electric vehicles arrive and depart based on these electric vehicle behavior distributions we have. We also have behind this chargers, we have some group of chargers that are connected to some local connections, maybe a transformer or a circuit breaker, something, let's say a constraint we have there. And then in between, we have a power network, where in this power network, we have to do some power flows, maybe check if the voltage violations, see if there are any voltage violations, etc. So we do this in a discrete manner, and in every step, our algorithm is called to select what are the charging actions. For example, I actually think we have a very nice visualization afterwards. But the idea is, yes, we do the simulation, we get some nice results, we get some replay files so we can repeat the simulation maybe with other algorithms and see what's going on. So that's an overview, a small-scale overview. We approach the problem from the perspective of a charge point operator or something similar. We have some chargers and electric vehicles arrive. This is a scenario, let's say, of public charging or a parking slot or many parking slots charging. So we see electric vehicles arrive, they have their SoC, we have some charger signals. Yeah, and we just do simulation. And in the end, we get some numbers, if we did well or not. Let's dive a bit deeper into how the parameters look like. We have, for example, the simulation parameters like time scale, simulation length, etc., scenario, number of chargers. Then we have a lot of simulation, a lot of parameters about electric vehicles, like AC, maximum charging power, minimum DC. You know that if you go to practice, in reality, there are a lot of limitations, like some LVs don't charge very low, others don't charge very high. So there are a lot of complex things that you can model if you want to. So we allow the users to simulate more complex things if they want to do that. We also have charging stations. Of course, you have some freedom to select things over there as well. And then we have the transformer also. So we also have the power grid parameters that we can customize. So the idea is that we have a modular and flexible software where if a user wants to change a module, for example, put another module for EV behavior, for another EV model, or another charger behavior, they can easily do that. Let's move forward into some of the other features we have implemented. For example, we have implemented a nice two-stage charging. So something we observed in some of the older electric vehicles is this constant voltage, constant current region. So we try to simulate it. So we use the more complex models to allow for more realism. Again, we have a battery degradation model to simulate how the battery is affected by doing V2G, which is also something very important and people are looking for in the research. And like I mentioned earlier, this is just some of the distributions that are openly available, so anyone can use them. And it's very important in creating realistic scenarios. So these distributions are very pivotal in our tool. Another aspect of realism, let's say, is we use real models, real electric vehicle models that exist. Like in this scenario, we have went to the RVO of the Netherlands and saw how many are the market sales of electric vehicles in the Netherlands. Yeah, and based on that, we can sample during the simulation and see how many of them can appear. So in 2023, we had a majority of Teslas, so we expect Teslas are going to appear more often in the simulation. Again, we can model a lot of different problems. For example, we also have the part of the grid. So in the grid, we have some inflexible loads, some PV production. So we are using some open source tools to allow to simulate this inflexible load and solar power, to add some extra realism there, and allows for some extra scenarios. And of course, we have some prices, charging prices. We can assume they're different from discharge prices. They can be the same. And then we can do some simulation and see what's happening there. Yeah, this is the latest tool I was talking about, is the voltage simulations. And as you can see, we can have any type of network we want here. We have buses, we have PV panels, we have loads. And in this way, we can simulate what happens to the grid, what is the impact of charging. And maybe we can design charging that helps the grid to alleviate voltage violations. So this is another aspect. If you can see, there are a lot of different things we have added in this simulator. You don't have to simulate all of these things. Maybe you don't care about very complex things. Maybe you just want to do some simple scenarios, just a parking lot. The thing is that the idea is that this is flexible and very modular, so the user has to select what they want to do. And yeah, something very important, it can support large-scale simulations. So as we can see here, we are simulating 10,000 charging points in the course of a week using a very simple charge as fast as possible charging strategy. And we see, yeah, the results are not very good, which makes us focus more on creating more good tools, on not having these very huge peaks. Yeah, I would like to move to the second project we're developing in the DRIVE2X project. It's a cooperation of many partners, like DLR from Germany, TNO, EDP from Portugal, and Salford University from UK.
Yeah.
Yes.
Thank you, Stavros. So maybe also before moving forward, important to something that maybe Stavros mentioned, forgot to mention here, is that the goal of the EV2Grid environment that we develop is from one side on education at the university, right? So students can directly focus on developing algorithms to tackle the technical challenges, specifically in this case, the large-scale problem of optimizing charging and discharging of a large number of electric vehicles. And from the other side, companies and enterprise can also test new algorithms with the ones that are already validated and available open source in this platform. So before moving to the next platform that we want to present also today, if you are interested into this development, we are also looking for partners, more users, use cases, and sort of create an open source community around the tools that we are also developing. So as Stavros mentioned, in this second tool, which is called EPIOT, Electromobility Prediction Interactive Open Source Tool, is a work in progress with many European partners as part of the DRIVE2X project. And what we want to do is to develop an open source API and also data sets, considering a sort of multimodal philosophy in which we collect multiple information around the city. So we have historic charging sessions, we have geographic information about the location of the charging stations, transformers, weather information, traffic data. And the idea is that we present all this information into a single platform that can later be used by different stakeholders. You can think of the CPOs for optimizing location of chargers. You can think of municipalities for optimizing location of public infrastructure, so public chargers, but also identifying synergies between traffic information, weather related to renewable generation, for example, and also congestion related to the information for in real time from the operation of the network. Within this platform, we are also developing machine learning models that will be the ones that will do estimation of the flexibility from electric vehicles. And we have other source of algorithms and tools that provide estimation and forecast of low profiles, flexibility, and other KPIs. So the access to the platform is here. This is an alpha version. We are still working on it, but it will look something like this. So here you see the particular case of Amsterdam, which is the one that we're using as a test case. So what you see over here is the city with the geographic location of the charger infrastructure. And what we do here is that we can select a particular geographic area within the tool. Within this particular area, we can identify, for example, the aggregated EV charging, making use of the machine learning algorithms that are deployed for estimating the flexibility coming from electric vehicles, but also the forecast of the demand from the EV chargers, but also from the consumption, from the demand in the transformers, in the medium voltage infrastructure. Another important feature, you can select the date of analysis, and over here you see the forecast of the low profiles. but also the different type of algorithms that you can test, right, in order to see the impact, for example, in the network. So you see as fast as possible, as late as possible, average power, and many other different type of charging strategies. So this kind of tool, of this kind of option, the idea is that it can be used by the municipality to see, for example, the need of procuring flexibility in a particular area of the city if smart charging is, for example, not available there. Here in this second window, you can see the flexibility. So we are still in development of how do we quantify the flexibility available for electric vehicles. And in this last part is more related to some KPIs, so performance indicators related to the users, the grid in terms of the impact, depending on the flexibility, on the smart charging, algorithm use. You see important statistical information related to the operation in order to make decisions. So this is a tool for making decisions. So just to conclude, we introduce two open source EV charging tools for large-scale analysis. Stavros introduced EV2G, which is focused on developing algorithms for dispatch of electric vehicle, fully customizable. You can deploy your own algorithms and then immediately compare with others that are already validated and available there. The second is the APO platform, which is developed for flexibility quantification from electric vehicles. It's a multimodal platform developed for support operational and strategic planning of city-level infrastructure, so electricity infrastructure together with EV infrastructure. And in this particular case, we saw some examples of Amsterdam, which is one of the cases for the DRIVE2X project, and we will be doing a demo later on in this European project. Thank you very much. If you have some questions, we're happy to answer. Any question? Yes.
Yes. What is exactly included in the forecast? And is, for example, also the smart agents for the charging points separately also included?
So the question is how we are doing the forecasting, basically, right?
Yeah. What is included is like the price incentives, whether that kind of things included.
All right. So the idea is that the core idea of this project is, of this work package, is how does the load profile of a charger here differ from a charger in the center? So we want to include some spatiotemporal information, for example, weather is global. In the case of a city, it's kind of the same. But other things that affect is, for example, the economic status of this area, or maybe the traffic. So in these models, we want to include this type of information so we can get very specific load profiles to these areas. Of course, we don't have access to real data. We're never going to get what actually happened the previous day, so we can predict there. Because this is an open source tool, we use open source APIs. But if a company or a municipality ever wants to go there, they have the data, so they can include them in the model, use the code for themselves, and then we'll have very good predictions. So the idea is that we use all this multimodal information like we mentioned here to try to get specific localized predictions. Yeah.
Okay, thank you.
Any other questions?
Are these mainly AC chargers?
Yes. Yes.
Are these mainly AC chargers?
Yes. So one of the limitations, let's say, of our selection is that this is just public charging stations. We don't include parking lots or fast chargers or. So yeah, this is just public charging stations at the moment. Maybe next
Public AC chargers.
Public AC, yes, correct. Yes.
Maybe a continuation. Do you have any? I think my voice is clear.
Yeah.
Okay. All right. So do you have any future plans to go into DC side or depot use cases?
Yeah, that's a good idea. We have a lot of thoughts. So we have more than 1 year to still get to develop new things. Mm-hmm. One of these ideas is to go to DC charging and see what happens to, what is the load profile of DC. The limitations we have is we don't have load profiles for them, open source at least. So this is something that we need to work on. And the other thing is we're also considering about V2G. What happens if these chargers were V2G?
Right.
What happens to the load profiles? What are the possibilities in terms of flexibility? So we also want to work toward there, towards the V2G part.
Right.
Even though, yeah, it's not coming soon, but maybe it comes one day.
Okay, good to know that. Thanks.
Yeah.
Hi. First of all, thanks for making this tool. I'm very excited actually to test it out. I had a question about the slide where you showed upwards and downwards flexibility.
Yes.
I was wondering,
How it's calculated.
yeah, especially because the charging strategy here is as fast as possible. So why is there upwards flexibility?
Because there are some times that you can choose not to charge. So the last step of every charging, I think it relates to that because of the last step. But it's very smaller proportional to the downwards. So this is a very, very simple flexibility model. Doesn't care about what happens if you charge now. How does it affect the flexibility of the future? So this model just says that the maximum power we can charge is a value. So the flexibility is how low we can go and how higher from this power. In this case, as fast as possible, we can go very little up. Actually, in very specific EVs, we can go up. But usually, we can just reduce the power. What we want to do is we want to have a more complex model that checks the flexibility as a polygon. So if we charge now, how does it affect the flexibility of the next steps? I hope it answers the question. Yeah.
I still have doubts. With delayed charging.
Yeah. Delayed charging and delayed flexibility.
Yeah, okay, yeah.
Yes. Yes, yeah. Yeah, it's because of the tail of the load profile, but we need to check it. I need to check it again to be sure that it is that.
So then the relationship between like the small amount of upward flexibility and the large amount of downward flexibility tells you something about the flexibility in terms of how much you can still shift?
Yes, yes.
Okay. Yeah, got it.
Yes, thank you. Oh.
Yeah, I also have a continuation about that flexibility topic. This shows like the absolute possible flexibility limits.
Yes.
It's also important here to consider that in real life, you actually won't be able to go even close to that because, like, imagine the future where everything is electrified and, like, there somewhere in the center of Amsterdam, there is electric ambulance that needs to be charged. You cannot not charge it. It needs to be charged. And real life will bring quite a lot of limitations on that picture that, to my opinion, can be quite optimistic. Because also the passenger cars, they expect that they can at any point go to grocery shopping and that their vehicles are charged and that they will be quite upset if apparently the grid needs some power and it's made by the cost of their convenience.
Yeah, very good point, of course. Yeah, I think this still lacks some realism, this approach, of course. In practice, yeah, you have some business models that take care of what you just mentioned. But yeah, it's something good to consider when we develop this tool. So yeah, thank you.
Maybe if I can complement that answer, it's more on who's the user of the tool, right? And in this case, it's more for planning purposes from the municipality and also the CPO's perspective. So there is a lot of discussion in Amsterdam, particularly because it's very crowded, the city center, or if new permissions needs to be granted for connections of chargers, private and public infrastructure. So what we try to do here is that, yes, we are not particularly defining the smart charging strategy. We're just seeing the impact on the network or the type of profile that will be expected, so the municipality can sit together with the operators, the EV operators, to discuss how to continue deploying this infrastructure. Yeah. Any other questions? If not, thank you very much for your attention.
Thank you.